Today we'll talk about a new data structure called Quadtrees and its application to meshing. Let's start as usual with an application. Here we have an image of a circuit board and the distribution of heat emission when this board is some under stress. From an engineering point of view, it would be very useful to simulate such a heat emission map given a design of a circuit board before actually producing it. To simulate such a heat emission map, we can use finite element method. We can use the finite element method by partitioning the board into small pieces and estimating the distribution of heat within each piece using some numerical methods. A finer mesh will lead to better approximation, and a coarser mesh will lead to faster computation. Finally, if the mesh pieces or elements are compact, that will lead to faster convergence of numerical methods. So the goal for today will be to develop methods of building a mesh given the design of, for example, a circuit board. We will want to build a non-uniform mesh, which will be finer close to the boundaries of the objects of our interest, and it will be coarser far away from the boundaries so that we can save on computation time. And we want the mesh to consist of well-shaped elements. In this particular case, we will be working with triangles. The triangles should not be too thin so that we can get a reasonable convergence time. Let's formalize the problem that we will consider today. We will restrict our consideration to objects that can be described with boundaries consisting of segments of limited number of orientations. In particular, we will consider octilinear polygons, and we will assume that their vertices are given with integer coordinates and the polygons are placed in a square of a large enough size. In particular, we will take the side of the square to be some power of 2. Our goal will be to construct a triangular mesh on this input with the following properties. First, the mesh should be conforming. Any two adjacent triangles need to share the whole edge between them. The example in the figure is a non-conforming mesh because, for example, this triangle and its adjacent triangle on top do not share the whole edge between them. They are only sharing part of their side. Secondly, the mesh should respect the input. That means that the edges of the triangles that we get should not intersect the edges of the polygons. And finally, we want the mesh to be well-shaped. We will restrict the angles of the triangles to be between 45 degrees and 90 degrees. And finally, we are interested in constructing a non-uniform mesh that has smaller triangles closer to the polygons and larger triangles further away from the boundaries of the polygons. A uniform mesh will simply have too many triangles to make computation efficient. Let's discuss the following question. To achieve our goal, do we need to introduce Steiner points in our construction? Meaning that, do we need to create new vertices of the mesh? Let's start with the well-shaped property, and let's consider the following task. Given the input, we will want to find a triangulation that maximizes the smallest angle. So please solve the following exercise. We're given an input polygon within a square, and we want to find a mesh that does not use Steiner points, meaning that we want to triangulate the interior and the exterior of the polygon here, such that the smallest angle is maximized. Have you constructed a triangulation that looks something like this? Even though we try to maximize the smallest angle, still we have some triangles with pretty small angles here. So indeed, without introducing Steiner points or new vertices, we cannot guarantee that triangles will have nice shape. Without Steiner points, our triangles may have very small angles, but with Steiner points, we can get a very nice, well-shaped mesh. Furthermore, we can even get a well-shaped and non-uniform mesh. Here, compare the uniform mesh on the left versus non-uniform mesh on the right, where on the left we have more than 500 triangles, and on the right we only have 52 triangles. As you can see here on the right, the closer we are to the boundary of the polygon, the smaller the triangles get. For our method of constructing nice meshes, we will use quadtrees. Quadtrees can not only be applied to meshing, but also to a variety of different applications. For example, in maps, they are used to smoothly navigate between different zoom levels. You can explore how Google Maps uses quadtrees by following the link below to the map tiler. So let's define this very useful data structure. To build a quadtree on a square, we will iteratively partition the square into smaller and smaller squares. And a corresponding quadtree will be a rooted tree in which every interior node will have 4 children, corresponding to the 4 quadrants that we get when we split a square into 4 pieces. Every node in the tree will correspond to a square in the partition. The parents will correspond to larger squares, and the children in the tree will correspond to the smaller squares. When we will be talking about the partitioning of the square, we will use the terminology of subdivision. We will have edges, vertices, and faces of the subdivision, but we will also talk about sides when we will be talking about the boundaries of the squares, and we will learn to traverse the partition by moving between neighboring squares. Note that the squares can be neighbors, even though in the tree the corresponding nodes will lie at different levels. Formally, for a point set P in a square Q, the quadtree can be defined with the following recursive definition. If the set P consists of one point or is empty, then the quadtree corresponding to the square is a leaf, storing that point set, either 1 point or 0 points. And if the point set consists of more than 1 point, then we will partition it into 4 smaller squares. The quadtree in this case is a root with 4 children corresponding to the 4 smaller squares, which we will denote corresponding to the directions north, east, west, and south. The point set will be partitioned by these squares into 4 subsets. For example, all the points of set P that lie inside the northeastern square will go into the set P northeast. Note that by definition, if a point lies exactly on the boundary between 2 squares, then it will be assigned to the left square or to the bottom square. Let's build a quadtree for this example. We start with a square that has more than 1 point in it. So the quadtree corresponding to this point set will be a root with 4 children, where each child will be a smaller square. Now, 2 of the squares are empty, and thus by definition there will be the leaves in the tree, but the other 2 squares again have more than 1 point each, and they will be partitioned further. So we will make the corresponding nodes in the tree parents, each having 4 children. On the northeast, each square now has either 0 or exactly 1 point, so all the smaller squares will correspond to a leaf. On the other hand, on the southwest, we have 3 squares with 0 or 1 point in them, which will correspond to a leaf, but there is 1 square that needs to be subdivided further, and thus the corresponding node in the tree will get 4 children. We will repeat this process until each of the smaller squares has exactly 0 or 1 point. So the tree on the right is a quadtree corresponding to the point set and the square subdivision on the left. Please find this exercise in the following page and construct a quadtree for the given point set. Remember, by definition, if a point falls on the boundary between 2 squares, then it will be assigned to the left or bottom square. Have you obtained this partition of the square and the tree? If yes, great job. If not, compare your solution to the one that you see on the screen. The recursive definition of the quadtree that we introduced in the previous video directly leads to an algorithm for constructing a quadtree. Let's develop some properties of quadtrees, and we will start with considering the depth of a quadtree. Let's consider the following question. If we know that a quadtree has n nodes, what can be its depth? We can prove the following lemma. If parameter c denotes the smallest distance between a pair of points on which we build the quadtree, and s is the size of the original square, then the depth of a quadtree built on that point set for that square is at most log of s over c plus 3/2. The proof of the lemma is the following. We start with a square of size s, and let's assume that it has some level I, meaning that its depth is higher than I. If there is a square at level I, its side length will be s divided by 2 to the I. Right? At the 0th level, the length of the square is s, so this corresponds to s divided by 2 to the power of 0. At the first level of the tree, we split the square into 4, so the side of each square is s over 2. At each next level, we subdivide the squares into 4, meaning that we reduce the side of the square by 2. Now, within a square at depth I, if there are 2 points, the maximum distance between these 2 points can be at most square root of 2 times the side of the square. So, if the depth of this square with 2 points in it is I, the distance between the 2 points in the square needs to be at least c by the assumption of the lemma, and that means that the diagonal of the square needs to be greater or equal to c. If we solve this inequality for I, we get that I is at most logarithm of s over c plus 1/2. And because the assumption was that this was an internal node with a square with 2 points in it, the height of the quadtree will be at most logarithm of s over c plus 3/2, so one more. Now we know how to limit the depth of the tree. If d is the depth of the resulting quadtree that is built on a point set consisting of n points, then it will have big O of d plus 1 times n nodes and can be constructed in the same big O of d plus 1 times n time. The proof of this is the following. Note that we can find the relation between the number of leaves in the quadtree and the number of inner nodes. Because when we are splitting a square, we are replacing a leaf with an inner node and 4 new leaves. That means that we are adding 1 inner node and 3 leaves. So we get the relation that the number of leaves in the tree will be 1 plus 3 times the number of inner nodes. And because all inner nodes correspond to squares that needed to be split, meaning those squares contained at least 2 points each, then at each level of the tree, we can have at most n squares corresponding to inner nodes. From these two observations, we can conclude that if d is the depth of the resulting quadtree, then we will have the order of d plus 1 times n nodes in total. Let's now discuss how to traverse the quadtree subdivision. Given a node v in the quadtree, we will see how to find its neighbors. We will do this on the example of finding the north neighbor. Consider the pseudocode. Given the node v of the quadtree T, we will find the deepest node v prime at the same level as v or higher than v, so that the square corresponding to v prime is the north neighbor of the square corresponding to node v. The algorithm is the following. We check if v is the root of the tree, then the root has no north neighbor and we return null. Otherwise, let pi be the parent of v in the tree. Now, if v is the southwestern or southeastern child of that parent pi, then we simply return the northwestern or correspondingly northeastern child of that parent pi. That is, if this is the parent pi and the node v corresponded to southwestern square, then we simply need to return the northwestern child of pi. And similarly, if v corresponded to southeastern child of pi, then we simply need to return the northeastern child of pi. On the other hand, if v was not the southwestern or southeastern child of pi, as presented here in the example, this is the square pi, then we recursively find the north neighbor of the parent pi. Here, this will be the north neighbor mu of the node pi. If mu does not exist, if it returns null, or if mu is a leaf itself, then we simply return mu. Or else, depending on whether v was northwestern or northeastern child of pi, we return southwestern or southeastern child of mu. The following theorem shows the analysis of the running time of this algorithm. If our quadtree has depth d, then a neighbor in any direction of a node v can be found in big O of d+1 time. To prove this theorem, we can observe that the depth of the recursion is order d+1. We are only moving up the tree when calling the recursion, and the cost per each recursive step is constant. Thus, indeed, the running time of traversing the quadtree subdivision by moving between neighbors can be done in order of the depth of the quadtree. A quadtree is called balanced if any two nodes corresponding to neighboring squares differ by at most 1 in depth. This is an example of an unbalanced quadtree. We see that there are two neighboring squares whose corresponding nodes will lie at depth further apart than 1. To make this quadtree balanced, we can subdivide some of the squares until all neighboring squares differ in size by at most 2, meaning that their corresponding nodes lie in neighboring levels of the tree. Consider the following algorithm to balance a quadtree. The input is a quadtree T and the output is a balanced quadtree T. We define a list L and put all the leaves of the tree in it. While this list is not empty, we do the following. We take any leaf from L. If this leaf is too large, then we partition it into 4 quadrants and add 4 leaves to the tree, and we insert the 4 new leaves into L. After that, if any neighbors of the old square are too large, then we also insert them into L. So we repeat this operation of subdividing the leaves until this list L is empty. When we're done, we return the balanced quadtree T. Now, take the quadtree that you built in the previous exercise and balance it. This is what you should have gotten as a result. Going back to the algorithm, how exactly are we deciding if a square is too large and if it needs to be subdivided, or if the neighbors of a square are too large and they needed to be added to the list to consider it later? Well, if two nodes of the tree are in the same level or in 2 adjacent levels, then their corresponding squares differ in size by at most 2. But if the nodes lie further apart, not in the neighboring levels, then, as we mentioned earlier, their corresponding squares will differ in their size by more than factor of 2. And this is exactly how we will determine if a square MQ is too large, if it has a neighbor of the size smaller than Q by more than a factor of 2, And similarly, if any of the neighbors, after subdividing Q into 4 quadrants, are too large, meaning any of the new squares are too small compared to the size of the older squares, we will add them to the list L. How many squares can we add by this balancing operation? Well, in fact, we'll show that given a quad tree with m nodes, we can balance it and obtain a balanced quad tree that will have an order of m nodes, and it can be constructed in order d plus 1 times m time, where d is the depth of the original tree. To prove this, we are going to make the following observation. While balancing the quad tree T, we will split its squares at most 8m times. Why is that? We will base our analysis on considering the old versus new squares. The old squares are the squares of the original quad tree T, and the new squares are the squares that we have introduced during the balancing operation. Consider a square sigma that gets split in the balancing operation. We will consider its 8 neighbors, so the squares that lie on the same level or above. We will claim that if sigma had to be split, one of its 8 neighbors will be an old square, meaning the square that existed in the original quad tree. We will prove this claim by contradiction. Assume that there are squares sigma that are split that do not have old neighbors, all their neighbors are new. Then we will consider the smallest such sigma. Among all of the sigmas that violate this assumption that one of their 8 neighbors is old, we will take the smallest sigma and arrive to a contradiction by finding that there must have been even smaller sigma with this property. Assume that sigma is the smallest such square that was split, with all 8 neighbors around it being the new neighbors. And let's consider the square sigma prime, which is the reason for the sigma to get split, meaning that sigma prime was split itself into the smaller quadrants and forced sigma to get split. Because all the 8 neighbors surrounding sigma by assumption are new, then the parent of sigma prime is new, and thus sigma prime itself is new. All these squares appeared during the balancing process. And now observe that these squares surrounding sigma prime are all new because they are contained in the squares which are neighbors of sigma, and all these squares are new by assumption. That means that sigma cannot be the smallest square with all neighbors being new. There is an even smaller square sigma prime that has all its neighbors new. Thus, our assumption is not correct, and if any square gets split, one of its neighbors must remain old. That means that we can use a charging argument and charge each split to an old neighbor. Each old neighbor will get at most 8 splits from the neighbors on the same level, and that means that at most there can be 8m splits. And now for the running time of the algorithm, when we are performing splits, we are searching among the neighbors of every node considered, and this we know can be done in order d plus 1 time. So if we are performing order m splits, order d plus 1 time each, the total running time is order of d plus 1 times m. Observe that some quad trees can be rather empty. They can contain very few points even though they have a lot of layers. For example, as in the figure. To save the space that is used up here for storing the empty squares, we could be using so-called compressed quad trees. What we're doing here is we're compressing the paths that consist of empty nodes. So this would lead to a linear size data structure. We're not going to consider compressed quadtrees here further though. Let's go back to the meshing problem. Recall that we are given a set of octilinear polygons with integer coordinates inside a square whose size is some power of 2. And our goal is to build a triangular mesh that is conforming, meaning that adjacent triangles share complete edges. The mesh respects the input. The edges of these triangles do not intersect the boundaries of the input polygons. The mesh is well shaped. We want all triangles to have angles 45 degrees or 90 degrees. And the mesh is non-uniform. We want it to be more fine around the polygons and more coarse the further away from the boundaries of the polygons we get. We will use quadtrees as a base of building such a mesh. So far, we have learned how to build quadtrees on sets of points. Here, the input are polygons. What do we need to adapt to make quadtrees work here? Well, let's partition squares until either they are empty or they are of unit size. When we reach squares of small size, the polygons, because they are octilinear, can intersect a square either going along the diagonal in the interior, or they can have a common edge with the square, or even a common point. For all of these squares, we will say that the polygons intersect those squares. So a square will be empty if none of the points of the square belong to the polygons. Let's consider this example. We are given octilinear polygons in a square with integer coordinates. We will start by subdividing the square into smaller and smaller squares until we reach either completely empty squares or until we get to unit-size squares. This is the resulting quadtree that we will continue working with. Observe that when we are done, if a polygon intersects the interior of a square, then it intersects it along one of the diagonals of the square. Now that we have this quadtree subdivision on top of the polygons, how do we get a mesh out of these squares? The first and naive approach would be simply splitting each square along a diagonal. But then we will obtain a non-conforming mesh. There will be some adjacent triangles that do not completely share the whole edge between them. Maybe then we can add vertices for each vertex of the square. Now we're getting triangles whose angles are too small. The solution to the question of how to get a valid mesh here is to first balance the quadtree, and then we will add Steiner points inside the squares if necessary. So first we will balance the quadtree, and then we will either split the squares along the diagonals, or if a square has adjacent smaller squares, we will add a Steiner vertex in the middle of the face and connect it to all the vertices of the adjacent squares, like here in the figure below. Let's formalize this algorithm in the following pseudocode. We start with a balanced quadtree T and the corresponding quadtree subdivision of the square Q, and we will output a triangulation of T. We start with a doubly connected edgeless representation of the quadtree subdivision, and for each face of it, if it is a unit square and its interior is intersected by one of the polygons, recall then this polygon will intersect the square along its diagonal, then we'll add this diagonal to a corresponding triangulation. And if a square is not intersected along a diagonal by a polygon, then let's consider the vertices of the adjacent squares. If they don't split any of the square's edges, then we'll simply add a diagonal. And otherwise, we'll add a Steiner point in the middle of the face and connect it to all the vertices of the square and also to the midpoints of the sides that are split by a vertex of adjacent squares. Finally, the algorithm to create a mesh starting with a set of octilinear polygons in the square with integer coordinates, we do the following. First, we create a quad tree on the input. We balance this quad tree, and finally we triangulate the balanced quad tree. Build a quad tree for this input polygon in the square, balance it, and then build a triangulation. Compare your solution to the one in the screen. To summarize our meshing approach, we conclude with the following theorem. Given a set of disjoint polygonal objects in a square of size U on a squared grid, we can build a non-uniform triangular mesh on this set of objects that will be conforming, well-shaped, and will respect the input. The number of triangles in such a mesh will be of order P of S log of U, where P of S is the total perimeter of all the objects, and the mesh can be constructed in order of P of S times log squared U time. To prove this theorem, first we analyze the size of the mesh. We'll start by counting the number of unit squares that intersect the boundary of the polygons. We observe that each unit of the perimeter of a polygonal object is adjacent to only a constant number of unit squares. That means that the number of unit squares intersected by the polygonal objects is proportional to the perimeter of these objects, but the same would be true for a coarser grid at any level of the quad tree. So, because the depth of the quad tree is logarithmic in the size of the original square U, we get that the size of the quad tree is proportional to the perimeter of the polygons times the log of U. This gives us the number of triangles in the final mesh. And for the construction time, building a quad tree takes linear time in the size of the quad tree. The balancing procedure adds an extra log factor to the running time, and the final triangulation step can be done in time linear in the size of the quad tree. This gives us a mesh with a number of triangles of order of P of S times log of U, and it can be constructed in time of order P of S times log squared of U. We conclude today's topic of quad trees and meshing with some discussion questions. First, the mentioned earlier compressed quad trees, can they be computed and updated efficiently? In fact, yes. Those will be called skip quad trees. They will have linear complexity and will support the update and search operations in logarithmic time. Refer to the cited paper for further details. Today we've mentioned 2 applications for using quad trees. Are there any other applications? Well, as mentioned earlier, quad trees are really widely applicable, and they find their use in a range of applications from computer graphics to GIS systems, and even in geometric algorithms they are often used to build approximation algorithms. Finally, our standard question, can this be generalized to higher dimensions? And indeed, quad trees are very easy to generalize to higher dimensions. In 3 dimensions they would be called octtrees, because now each cube will be subdivided into 8 smaller cubes.